Hello all, in this lesson we're going to study the way the number of particles can affect pressure in a container. So before you learn anything about this topic, I wanted to show you a couple of really cool videos I found on YouTube that demonstrate the power that the number of particles has on pressure. All I want you to take notes on these couple of videos are the procedure that you seem to see, and if you have an idea about what's happening, then of course write that down. And this one's too wild to even introduce, so just enjoy.
760. Gewonnen hat Herr Dr. Hilsch.
So there's no homework associated with this lesson, but I do need you to copy down this aim on a separate piece of paper, which will become classwork for this lesson. And underneath the aim, these do now questions, of course. Don't forget to fill in your graphic organizer for essential questions. For this unit, remember our essential question is, how can we describe matter in terms of stability and change? Alright, so you remember from the previous lesson that particles exert pressure when they collide with the walls of their container. And it also stands to reason that the more particles you have inside a container, the more collisions would be occurring. And if collisions cause pressure, then more particles would cause more collisions, which would cause more pressure. Okay, so let's talk about that some more. Pressure versus number of particles. So I'll show you this animation in class tomorrow, but basically the first one has more particles on it with more collisions, and the second one has less particles with less collisions. The pressure in the first scenario, if we assume that each particle can exert one pressure point through one collision, then it would be 1, 2, 3, 4 different collisions, or 4 pressure points. It's a made-up unit, so I'll just call it PP. The pressure in the second scenario, however, is less because there are only 2 collisions. So 2 pressure points. So what caused the difference in pressure in the 2 scenarios is literally just the number of particles. So the graphical relationship between pressure and number of particles is a really nice way to see this effect. This is going to be called a directly proportional relationship, which you probably have studied in math class, but it basically just means that as one factor increases by 1 unit, another factor increases by a proportional unit, not necessarily 1 unit, and it's always going to be like that. So I have a couple of sort of fantastical examples. Example or not. For every knife wound inflicted, a victim loses 1 cup of blood. Does that meet this relationship? I would say yes, because 1 knife wound is 1 cup of blood loss. Or alternately, example or not. For every knife wound inflicted, a victim loses a smaller and smaller amount of blood until all the blood is gone. I would say no, not an example, because every time there's a knife wound, there's a different amount of blood being lost, so I don't think that's directly proportional. So we know that the more particles you have, the more collisions you have, and the more collisions you have, the more pressure you have. And in terms of logical statements, that is a direct proportion, because it's saying the more you have of this, the more you have of that. So again, this is probably something you have already learned in math class, but directly proportional relationships will have slopes that are constant and straight lines when you graph them. There's no rule about the size of the slope though, so it could be a low slope or it could be a very high slope or even higher, but just know that the slope is going to be constant and unchanging. So I can show you this animation tomorrow, but I also am going to show you a demonstration tomorrow that is the inspiration for this animation. But let's take notes on it now and get familiar with the concepts. I still think the demonstration will be just as amazing when you see it in person. But remember, the number of particles relates to the number of collisions, which relates to the amount of pressure. And outside this can, I see 1, 2, 3, 4, 5 particles, and inside there are also 5. So you're going to have equal pressures inside and outside. We can say pressure points again. Now, as long as this is true, they're equal, then the can is going to be stable. But one thing you can do is you can put a little bit of water into the bottom of the can and boil it. And what happens is, as the water molecules escape, creating water vapor, they can push the air outside of the can. So suddenly, where you used to have air molecules inside the can, now you have a vacuum. And once this vacuum is created, if I were to seal the top of the can, then the water molecules that are existing as vapor would condense back to liquid, and there would be nothing left inside the can, and all you would have left are the collisions from the air molecules that are outside the can in the atmosphere. And if all the pressure is pointing from outside in, then the can would no longer be stable and it would collapse. So this is actually the concept that was being demonstrated in the introductory videos of the 55-gallon steel drum and the tanker truck. Essentially, they had the air from the inside of the containers removed. In the case of the steel drum, they did it exactly the way that's been described here, just with water in the bottom and boiling. But in the case of the tanker truck, they had to evacuate the air with a physical vacuum. But both have the same effect, which was that the pressure outside those containers was much larger because of the pressure of the atmosphere, and the pressure inside was much lower because of the absence of particles and the absence of collisions. And therefore, in both cases, the structure imploded. I also made a note down here about the difference between implosion and explosion. It's a pet peeve of mine that those two words are used interchangeably by some people. So just know that implosion means to collapse inward, where explosion would mean to expand outward. And we've reached the pair-up, so just copy down these questions from the pair-up, and we'll answer them in class tomorrow after the demo. And also grab these summary questions. So you should have Cornell notes for this lesson, and your classwork page should have today's aim, a do now, the pair-up questions, and the summary. Thanks for watching.